Imagine the coldest temperature possible. Can you envision it? We often think of freezing blizzards or the icy plains of Pluto. But what about something far colder? What about a temperature so low that all motion ceases to exist? This, my friends, is the realm of absolute zero. Absolute zero rests at a bone-chilling minus 273.15 degrees Celsius, or 0 Kelvin. It's a point on the temperature scale that has fascinated scientists for centuries. This isn't just about reaching for the coldest temperature, it's about exploring the fundamental nature of matter and energy. But here's the catch: absolute zero is a destination we can never truly reach. It's a tantalizing frontier, always just out of grasp. Why is that? Why does the universe conspire to keep this ultimate coldness beyond our reach? Let's dive in and explore the fascinating science behind this cosmic puzzle. To understand why absolute zero is unattainable, we need to understand what temperature truly represents. At its heart, temperature is a measure of the average kinetic energy of particles within a system. In simpler terms, it's a gauge of how much things are jiggling around. The hotter something is, the more frantically its atoms and molecules are vibrating and colliding. Conversely, as we cool things down, this molecular dance slows down. Think of a bustling city street versus a quiet park. The city is abuzz with energy, much like atoms at high temperatures. The park, however, offers a sense of stillness, mirroring the slowing motion of atoms at lower temperatures. Now imagine taking this cooling process to its extreme. As we approach absolute zero, the movement of atoms and molecules would slow to a virtual standstill. It would be as if the universe itself were holding its breath. But as we'll soon see, reaching a complete standstill is where the laws of physics step in, throwing a wrench into our plans for achieving absolute zero. Our quest to understand why absolute zero is unreachable leads us to the realm of thermodynamics. Specifically, the third law of thermodynamics throws down the gauntlet, setting a fundamental limit on how cold we can get. This law states that the entropy of a perfect crystal at absolute zero is zero. Entropy, often described as a measure of disorder, implies a certain randomness or freedom in how energy is distributed within a system. A perfect crystal, with its atoms arranged in a flawless repeating pattern, represents the ultimate state of order, hence zero entropy. Here's the rub. To reach absolute zero, we would need to remove all the heat energy from a system and perfectly order its constituents. However, the third law tells us that as a system approaches absolute zero, it becomes increasingly difficult to remove heat. The energy states within the system become so tightly packed that extracting that last bit of heat is like trying to squeeze water from a bone-dry sponge. It's virtually impossible. Section 4. Quantum whispers, uncertainty, and the dance of particles. As if the third law of thermodynamics wasn't enough of a hurdle, quantum mechanics throws another curveball into our quest for absolute zero. Heisenberg's uncertainty principle, a cornerstone of quantum theory, states that we can never simultaneously know both the position and momentum of a particle with perfect accuracy. What does this have to do with temperature? Well, remember that temperature is a measure of particle motion. If we were to somehow reach absolute zero and completely halt the motion of all particles, we would know both their position, stationary, and momentum, zero, with perfect certainty. This, according to Heisenberg, is a big no-no in the quantum world. The uncertainty principle ensures that even at extremely low temperatures there will always be some residual, unavoidable quantum fluctuations in the energy and motion of particles. This inherent quantum jitter prevents us from ever reaching a state of absolute stillness. Section 5. The cooling challenge: technological limits on the road to absolute zero. So, we have the laws of physics setting up some pretty formidable roadblocks on our journey to absolute zero. But what about our technological prowess? Surely, with our ever-advancing tools and techniques, we can come tantalizingly close to this ultimate coldness, right? Scientists have developed ingenious methods to reach ultra-low temperatures such as laser cooling and magnetic trapping. These techniques have allowed us to cool atoms to fractions of a degree above absolute zero. However, the closer we get, the more challenging it becomes. Imagine trying to grab a feather floating in a gentle breeze. Now imagine that breeze getting exponentially stronger with each attempt to catch the feather. That's a simplified analogy for the challenges faced in ultra-low temperature physics. The techniques used to remove heat become less effective and more susceptible to external influences as we approach absolute zero. It's a constant battle against the universe's inherent tendency towards thermal equilibrium. Section 6. A universe of discovery, unveiling the wonders of the ultracold. While reaching absolute zero remains an elusive goal, the pursuit of this unattainable temperature has yielded incredible scientific breakthroughs. In these extreme cold environments, matter behaves in bizarre and fascinating ways, defying our everyday intuitions. One striking example is the creation of bose-einstein condensates, or BCs. In a BC, atoms are cooled to within a hair's breadth of absolute zero. At these temperatures, the atoms lose their individual identities and begin to behave as a single, unified entity. It's like a stadium full of individual fans suddenly transforming into a single giant organism. Research into BCs and other ultra-cold phenomena has led to advancements in precision measurement, quantum computing, and our understanding of the fundamental nature of matter. So, while absolute zero remains out of reach, the journey towards it has opened up new avenues of scientific exploration and illuminated the universe in ways we never thought possible. Section 7. The Unending Pursuit, Absolute Zero, and the Frontiers of Science. Absolute zero, the ultimate coldness, stands as a tantalizing enigma in the vast expanse of scientific exploration. It's a destination we can never truly reach, yet its allure lies not in its attainment, but in the pursuit itself. Like a cosmic mirage, it beckons us forward, pushing the boundaries of our understanding and driving innovation. The quest to reach absolute zero has revealed the elegance of fundamental laws, from the elegant dance of thermodynamics to the perplexing realm of quantum mechanics. It has spurred technological advancements, allowing us to manipulate matter at the atomic level and peer into the heart of the ultracold. While absolute zero may forever remain an unattainable frontier, its pursuit has enriched our understanding of the universe and our place within it. And that, my friends, is the true wonder of scientific exploration. The journey often yields far greater treasures than the destination itself.